Welcome to the 10th week of live interactive session on the course Integral Transforms and Their Applications. So, today we will be discussing about the special transformation, the Radon transform. So, I will be going through some basic demo problems related to the Radon transform. So, I hope before coming to the session you all have watched the lecture videos for the week. So, you will basically should have an understanding of the transformation and its properties, how to use it. So I will be particularly going through some uh, some sample problems which using some of these properties and also which will be helpful for you to solve your assignment problems, and also will help you understand the concept much better. So without wasting time, so we will move to the first problem. So I have the function f of x comma y is equal to exponential of minus x square minus y square. Find dou f cap by dou u k, which is basically partial derivative of the Radon transform of the function f with respect to one of the direction cosine uk. So it can be any of the direction cosine. So we have two direction cosines here because it's a 2D problem. So x direction and y direction. So u1 will be cos theta and u2 will be sin theta. So we are asking a general derivative with respect to either of the direction cosine. As I mentioned, the f cap here represents the Radon transform of the function f. So options are given, so I may wait for a moment for you to try this out, and then I will start explain how we can do this. So use the properties. So meanwhile I will write the general definition of Radon transform in the 2D case. So if you have function f of x comma y, it's a two-dimensional, so it's a function of two variables. So its a Radon transform will be, so f of x comma y multiplied with the delta function p minus x cos phi minus y sin phi. So then we have to integrate it dx dy, where x and y can be integrated in the entire real domain. So this will give the Radon transform of the function f of x comma y in the variables p comma phi. So this is one of the definitions. So we can modify this definition a little bit, so we will get some other form of the same transformation. So in another representation will be f of x cos phi. Okay, let me verify the definition before writing. The same function f of p cos phi minus s sin phi comma p sin phi plus s cos phi into ds integral minus infinity to plus infinity. Okay, so this is what we represent using f cap of p comma phi, where the direction cosines u1 is cos phi and u2 is sin phi. So I hope this is like the basic that you might have already watched in the lecture video. So you should have a basic knowledge of this expression. So here so basically Radon transform represents projection of the function f of x comma y to a line or a plane. So here we are in 2 dimensions, so the projection we are doing it in on a line. So the line is represented using the along the line we measure the distance using the variable s here. So that's why we are integrating through the variable. So we are projecting it, and and we are seeing how the projection look like. So that's basically Radon transformation is. So so I hope you guys have tried doing this. Anyway, I will start explaining how we can do this. So first of all, the function so this is asked for the derivative of the Radon transform. So first one of the properties we can use is that like if you have watched the videos, you might have noticed this property that let's say there is a function f, its Radon transformation is let's say f cap of p comma phi, then its derivative with respect to any of the direction cosines can be evaluated as, let me write the property. As minus dou by dou p of f the Radon transform of the function multiplied with xk, and then basically we are then taking the partial derivative with respect to p. So this is the property we can use to evaluate this particular problem. So here we have the function f as exponential of minus x square minus y square. So first we need to evaluate it's a transform f cap of p comma phi, which is the Radon transform of the function exponential of minus x square minus y square. So in the lectures it's already shown how we can evaluate this. So anyway, I will once again go through this. So it's exponential of minus x square minus y square. Then basically we are integrating over the line for the variable s equal to minus infinity to plus infinity. So here notice that x is actually p cos phi minus s sin phi, and y is p sin phi plus s cos phi. So if you evaluate, basically this is if I group it, it's minus of x square plus y square. So we want x square plus y square, so which will be p square. So from these expressions we can evaluate p square cos square phi plus s square sin square phi minus 2ps sin phi cos phi. This is x square, and now y square is p square sin square phi plus s square cos square phi plus 2ps sin phi cos phi. And you will see this sin phi cos phi times will cancel, and the remaining times will add up to p square plus s square. So x square plus y square is just p square plus s square. So that's why this integral we can actually represent as f tilde of p comma phi is just the integral of minus infinity to plus infinity exponential of minus p square plus a square ds. And exponential of minus p square we can take outside because p is not an integration variable here. The remaining integral is just a Gaussian integral, and you know the answer, it's just square root of pi times e raised to minus p square. So this we can until this we can do, but actually to evaluate this particular problem we are using this expression. Okay, so in that we just don't want the Radon transform of the function f, but we want the Radon transform of xk times f of x if you see the right hand side. So that is like we want the Radon transform, let's say for k equal to 1 we want the Radon transform of x1, which is just a x only, x times the function, which is exponential of minus x square or minus y square. So I hope you understood what I am saying. So first we are evaluating this quantity xk times f of x, its Radon transform. Then later we will take its partial derivative with respect to p to obtain basically the right hand side, which will give the solution or the solution of the question. So for k equal to 1 is just this is a quantity we want to evaluate. For k equal to is just y, is x2, we are calling it as y, exponential of minus x square minus y square again. So like from this we can generalize the expression of Radon transform of xk times exponential of minus x square minus y square. So if you want to evaluate the first quantity for k equal to 1, if you use the same expression with just minus infinity to plus infinity, so the integral of this quantity, right, x into exponential of minus x square minus y. So I will just substitute for x is just p cos phi minus s sin phi, we already know that. So it is just p cos phi minus s sin phi times exponential of minus x square minus y square, we told it will reduce to minus a square minus p square, then ds. So let me remove this okay. Now we will split this into two integrals and take the constants of the integral outside. So it's exponential of minus p square, p can come outside, and also cos phi will come outside. It's exponential of minus a square ds minus infinity plus infinity, then minus exponential of minus p square sin phi minus infinity plus infinity s into exponential of minus a square ds. And you see this is actually an odd integral, this one, so odd integral, so its value will be 0. Okay, that will go to 0. The remaining integral on the left hand side, it is just p cos phi exponential of minus p square times the Gaussian integral, which is just square root of pi. So which we can also written in terms of p root pi p. Cos pi is the direction cosine u1 times e raised to minus p square. Similarly for k equal to 2, if you evaluate the Radon transform of which is xk is now y, right? So it's y times exponential of minus x square minus y square. You will see the similar expression you will be getting, but it will be just cos phi will be replaced with the sin phi. Okay, so p sin phi exponential of minus p square root pi, or you can also write in terms of the direction cosine, so it's a root pi p u2 exponential of minus p square. So generally for any k you can write the Radon transform of xk times exponential of minus x square minus y square as root pi times p times uk times exponential of minus p square. Okay, I think that is clear. So from this 192, like we are substituting for k equal to 192, we generalize the Radon transform of this particular quantity. Now from the expression 1, we can evaluate the left hand side using the expression on the right hand side. So from 1 we can evaluate dou f cap by dou uk, which is actually minus dou by dou p of the Radon transform, which is we have in 2. Okay, so which is minus dou by dou p of root pi times uk times p e raised to minus p square. So here you see only p is a variable with respect to the partial derivative, so we will take the constants outside and take the derivative with respect to p. It will be p exponential of minus p square minus 2p minus exponential of minus p square, plus. I can simplify this to root pi uk exponential of minus p square times 2p square minus 1. So this is how you can evaluate what is asked in the question, dou of cap by dou uk. So is this clear?
Yes, sir, it is clear, sir.
Okay, good. So I think the option B is the answer. Yes. Okay, so now we'll move to the next question. Find the Radon transform, the function f of cx. So x is a normal vector, let's say x1 to xn, having n variables or n dimensions, and c is some scalar which is multiplying f. Assuming, let's assume for this case c is a positive number. If c is a negative, we need to accordingly redo some things, but let's assume it is positive. And we just need to find the Radon transform. Here R represents Radon transform, also the cap in the options represents Radon transform. So actually the similar version is already given in the lectures as a property, properties of Radon transform. So here I'm just asking again how you can show this. So you can try this. I will wait for a moment, and if you find the answer, you can just comment in the chat box, or you can unmute and tell yourself. Then I will explain how we can do this. So hint is that you can use the basic any one of the definition of the Radon transform and then modify it accordingly. So you will end up in some answer. Okay, so you can try this out. I will wait for a moment. So I will now explain how we can do this. So from the basic definition, the Radon transform of any function, generalized version, let's say f is a function of the vector x. So here note that the bold x denotes a vector. Okay, and so the definition is it's actually f of x multiplied with the delta function p minus x dot u, where u is the direction cosines in that particular dimension. So in 2D we will have 2 direction cosines, in ND we will have n direction cosines, generalized form. Then dx, basically the dx in each direction, dx1, dx2, etc., dxn. So we'll have n of them. Similarly, n integrals here in all the directions from minus infinity to plus infinity. So we'll have n of them. Okay. All of them is from minus infinity to plus infinity. So now here we are asked for f of cx, a scaled function, and asking for its Radon transform. So in the definition, change which is going to come is here only, f of cx times delta of p minus x dot u, and then again dx1, dx2, etc., dxn integrals. So what we can do is that we can use properties of integrals. Like we can, let's say, so cx is a now vector. So you see cx will have components cx1, cx2, etc., cxn. Okay. Yeah. So we can say that cx is another vector, let's say y vector. So the x vector is just y vector by c, scaled, so that every dx components will be like dx1 will be dy1 by c, dx2 will be dy2 by c, like that everything will be scaled, so that this definition will just become, let's say I'm using a short notation for the integration. Let's say single integral I'm using, but okay, single integral over the real, the n dimensional real line or the real space I'm using, and f of cx I can write it as f y vector, and delta p minus x I will write as y by c, then taking a dot with the direction cosine. Then similarly here also I will use it's a dx vector as a general representation of the dx1, dx2, dx3. So here you can see this by the definition is actually the Radon transform of the function f, but in the variables. Okay, so basically one thing I forgot to say, yeah, dx I should be replaced in terms of dy. So if you see it's dx1 I should replace as dy1 by c, and then dy2 by c, etc., dyn by c. So basically I can take so there will be n such a c's multiplying in the denominator. I can take them outside because they are constants. So it will be 1 by c raised to n times integral over the n-dimensional real space f of y vector delta p minus y vector dot u by c, then dy1, dy2, etc., dyn. So this by definition is actually c raised to minus n times, it's actually the f cap in the variables p and y by c, sorry, u by c, where u represents the direction cosine. So so in that sense the option A will be correct answer. So is this clear? So after this we could,
Yes, sir, clear.
Good. So we could have stopped here, but let's continue with one more like step, so that we will get one more expression which is also correct in this options. That's why I'm continuing. So let's say this is expression 1. So the expression 1 I can again rewrite as, so 1 by 0 to n is already there outside. So it's f of y vector and delta, so if you cross multiply this times, is delta pc minus y dot u by c times dy1 dy2 etc dyn. Now you know the property of delta function. Delta of ax is 1 by mod a times delta of x. So we have here delta of some quantity by c. Basically delta is the quantity inside is scaled by 1 by c. So and we already stated that c is positive, so this will become this delta function alone can be written as c times delta of pc minus y dot u. Okay, so then again the dy1 dy2 etc dyn, this c along with the c raised to n outside will can be written as c raised to 1 minus n, because c is a constant, we took it outside. The remaining quantity, so let me write the c outside. Yeah. So whatever remaining is another definition. In another form, it's a definition of again the Radon transform of the function f, but now the variables are pc and u. So in that sense, we have option B also as a correct answer. So I hope this is clear. Actually simple one, and we are just using the property of not the property, actual basic definition, but then just modifying certain terms, that's all. So if it is clear, we will move to the next problem then. So find the Radon transform of the function x square plus y square times exponential of minus x square minus y square. So like we have seen the earlier problems, you can use the basic definition, and then you can show you can find which one is the answer. So I'll wait for a moment for you to try this out, and then I'll explain how to do this. Okay, now I will explain how we can do this. So like we have seen earlier, we will use the basic definition, which is the Radon transform of any function f of x comma y. So I have told two of the expression, one involving the delta function, one is the general form like f of x comma y times ds. We are integrating over the line which containing the along the directions. So where x we can substitute in terms of p cos phi minus s sin phi, and y we can substitute as p sin phi plus s cos phi. So so here we basically have the function x square plus y square times exponential of minus of x square plus y square. So basically we need x square plus y square. As I shown earlier, we can come to a conclusion that this is p square plus a square only. So the Radon transform of the function x square plus y square times exponential of minus x square plus y square is basically p square plus a square times exponential of minus p square plus a square times ds integral minus infinity plus infinity. So we are integrating over s. We can split it into two integrals. First one is p square e raised to minus p square integral minus infinity to plus infinity e raised to minus s square ds. Second one is exponential of minus p square minus infinity plus infinity s square e raised to minus s square ds. So both the integrals are even integrals, so they will have finite values. The first of one we know is just the Gaussian integral, so its value will be square root of pi, then e raised to minus p square. The second integral, s square e raised to minus s square ds. So for that we can use another trick. So we have, let's say, generalized version of the Gaussian integral exponential of minus a s square ds integral minus infinity plus infinity. We know its value going to be square root of pi by a, or square root of a. So by substitution we can evaluate this basically. So now if you take derivative of this particular equation with respect to a, okay, on both sides, so partial derivative with respect to a on both sides will give minus infinity plus infinity exponential of minus a s square times minus s square ds. On the right hand side, which is equal to square root of pi, it's a raised to minus r, right? So it's minus 1 by 2 a raised to minus 3 by 2. Or if you simplify this, we'll get a square e raised to minus a s square ds integral minus infinity plus infinity is root pi by 2 a root a, like that. So here we have an expression with a being 1. So s square exponential of minus a square. So we will get a solution which is square root of pi by 2 and a root a will be just 1. So solution will be that much. So we'll simplify this exponential of minus p square root of p, then 2p square plus 1 by 2. So that's all. So solution will be option D. So is this clear? So basically we are using the definition and just revising some of the old integrals that we know, like the Gaussian integral and and one more integral which is derived from the Gaussian integral, or easily can be evaluated from the Gaussian integral. So I hope that is clear. So we'll move to the next problem. So find the Radon transform of the square function f of x comma y is 1 for every x or y in the interval minus a to a and 0 otherwise. So it's like f of x comma y is 1 for every x or y in the interval minus a to a and 0 otherwise. So it's a piecewise function, so the distribution in the so this will actually plot a surface in the three-dimensional plane, and that will look like something like this. It's a rectangular box. So you see these values 1 and this the surface is 0. So this is basically the function. Okay. There will be axis. Let me draw the axis. So yeah, now the values here it will be a, and this will be minus a, 2n's. So this is a function, and basically the function is valid when x is minus a2 plus a and y is minus a2 plus a. The function has a particular definite value 1. Outside that interval it is 0. That's the meaning of the function. So we just need to validate the Radon transform. So from the definition, just the Radon transform of the function is just the integral of the function just 1 times the delta, which is delta of p minus x u1, which is x cos phi, then y u2, which is y sin phi, dx dy, where x is so the function is 1 only in the interval minus a to plus a for x and y. So x is going from minus a to plus a and y is going from minus a to plus a, and the function is 0 in the other domain. So basically that integral will become 0. So we actually splitted the integral from minus infinity to plus infinity into the integral in that particular box region, minus a to plus a, minus a to plus a, both in x and y, and the integral over outside, but outside it is 0. So that's why that integral explicitly doesn't appear here. So it's like we have done the same thing for Fourier transform or Laplace transform of the Heaviside function, step function. So same idea here also. It's a box function in 2D, so related to the Heaviside function. So now we need to perform this integral. So what we can do is that so this is a delta function, and which is involving too much complicated parameters like x cos phi, y sin phi, which is subtracted from the value p. So we know that this is going to be delta functions integrals will be finite if the in some parameter of the integral, it will delta function will pass through the value 0. The argument is 0, then only its value will be finite. Otherwise it is 0 everywhere. So that we know, but to apply that at this particular moment will be complicated. So we will use a simple method, that we will use an integral representation of delta function. So we know that delta of x can actually return as scaled integral. It's from the Fourier transform. So Fourier transform of 1 is actually delta function. So we are using that property. Exponential of minus ik x dk. So we will use that here. So Radon transform of f of x comma y is minus a to plus a, minus a to plus a, 1 by 2 pi integral minus infinity to plus infinity e raised to minus ik times in the place of x we have to substitute this entire expression. This is p minus x cos phi minus y sin phi, then dk dx dy. So what we do is that we rearrange the expressions in the, so basically the 1 by 2 pi we can take outside, it's a constant, and the inner integral over k will move to outside. Okay, so accordingly the outer integrals x and y we are bringing inside. So whoever is independent of x and y we can keep along with this integrals, like exponential of minus ikp, which is independent of x and y, and now so ikp times dk, and then x alone, like the part which contain x alone, we can take it like exponential of minus ik x cos y, yeah, plus ik dx, and another integral is there which is independent of x or p, like it's depend only on y, which is exponential of ik y sin phi dy. So so the outer integral will keep there, e raised to minus ikp dk. So the first integral on the inside I can integrate it, just an exponential integral, so sorry, integral of an exponential. So e raised to I kx cos phi divided by the derivative of the numerator, which is with respect to x, it's ik cos phi, and we need to apply the limit for x is going from minus a to plus a. The other integral, similar way I can find it's iky sin phi by ik sin phi, where y is going from minus a to plus a. Now we can take outside the constants like 1 by 2 pi. Cos phi and sin phi, they are constants basically, so that I'll take outside cos phi sin phi. Then the expression minus and plus into e raised to minus ik pi. K square is also a constant, so I will take the k square. So k square is actually not a constant in terms of the integral over k, but rather it is a constant when we are applying the limits for the inner integrals. Okay, for the inner integrals they are constant, so I will take that outside. And also one thing, now we apply the limits e raised to I ak cos phi and as e raised to minus I ak cos phi divided by I their axis. Similarly, e raised to I ak sin phi minus e raised to minus ik sin phi divided by I exists, and then the dk also exists. So we'll do one thing, we'll multiply 2 here and 2 here, so total 4. We'll multiply here also, and so with that we'll simplify this a little bit. So here 4 by pi, the 2 sin phi and cos phi we can group together to sin 2 phi, and then the remaining integral minus into plus infinity raised to minus ikp by k square. So you see the form, right? It's exponential, difference in exponential, exponential of theta minus exponential of minus theta by 2i, which is sin theta. So that's we are using that particular form. So e raised to theta minus e raised to, sorry, e raised to I theta minus e raised to minus I theta by 2i is sin theta. So we are using that expression here, sin of ak cos phi, then again sin of ak sin phi, then dk. Now you see here the integral is from minus infinity to plus infinity, and we have a sine times sine, so which is in terms of k it is actually even function. Similarly, this is k square is an even function, then only exponential of minus ikp is multiplying it. So if you expand the exponential of minus ikp, it will be cos kp and sin kp, and the cos kp is an even function, sin kp is an odd function. So basically this will split in two integrals. One of them is an odd integral which will anyway vanish, the other one is an even integral which only remains. So we do that here. So it's 4 by pi sine 2 phi, and since the even integral we can split it into like 2 times the integral from 0 to infinity. So it's cos kp sine of ak cos phi, then sine of ak sine phi by k square dk. So this 4 into 2 we can combine to 8. So here okay, let me keep it as 4 times 2, and so we will now use the property of the trigonometric functions that we will use. Let's say this expression we will call as okay, expression 2. Okay, now we will use the expression 2 sine a cos b, which is just sine of a plus b plus sine of a minus b. So from 2 we'll continue, which is equal to 4 by pi sine 2 phi times the integral 0 to infinity. So let's take this cosine sine to group together along with this 2. So 2 cos kp or 2 sine ak cos y times cos kp, we'll write it as sine of ak cos phi plus kp, then added to sine of ak cos phi minus kp. Then the remaining part sine ak sine phi there exists divided by k square then dk. Now we can split it into two separate integrals, both having identical forms. We will come to that. So 4 by pi sine 2 phi, first integral is 0 to infinity sine of k times p plus a cos phi times sine of k times a sine phi by k square. Then another integral which is sine of k times p minus a cos phi, the minus in front, and then again sine of k times a sine phi. So here dk is also, and then dk by k square 0 to infinity. So let me call this expression 3. Okay, so from here we will use a generalized integral. So basically we want integral of the form sine of ak, or let's say ax, and sine of bx by x square dx 0 to infinity. So we want an integral of this form. So we can actually find it from the table of integrals. Refer to Gradstein and Reichik, the book which contains the table of integrals. You can evaluate this, or you can find this value to be, it's basically pi by 4 times absolute value of a plus t minus absolute value of a minus t. So we will find this is the expression. So we will use that expression here. Sub in 3 we will find. So from 3 we will continue. It's like 4 by pi is there, 1 by sine 2 phi there, and then from this integral we will have a pi by 4 constant coming outside. For both the integrals it's a constant, so we are taking it outside, and then The remaining things we can manipulate, like p plus a cos phi added to a sin phi, then absolute value, minus p plus a cos phi minus a sin phi, absolute value. Then in the second integral, it says p minus a cos phi is added to a sin phi mod, then subtracting p minus a cos phi, then minus a sin phi. So if you find any mistake, please tell. So I am assuming there is no mistake, so I am just going ahead, probably sign mistakes or something. So here we are subtracting the second time from the first, basically the second integral from the first, so there will be a sign alteration like this. Now we will cancel the constants pi by 4 and rearrange it. We will find the solution to be p plus a cos phi plus a sin phi, absolute value, plus p minus a cos phi minus a sin phi minus p plus a cos phi minus a sin phi minus p minus a cos phi plus a sin phi, absolute value, the whole divided by sin 2 phi. So this is a solution. So is this clear? Any questions in this? So we are evaluating the Radon transform of the box function, which is 1 and 1 inside the box and 0 outside the box, which has a width of 2a, symmetrical from the origin. So basically we are using a definition of delta function. So basic definition of the Radon transform, which contains a delta function, and then we are substituting the definition of delta function in terms of a Fourier integral. Then basically 3 integrals will appear. If you change the order of the integration, the integral over the entire real line minus infinity plus infinity will come outside. The other 2 integrals we can simplify, which is inside, and then it will become like integral of the product of signs, some manipulations, and then from the table of integrals we will find the solutions, apply that, we will get the solution. So I hope that is clear. So basically what we found is that the projection of the box function to a plane or a line will have this kind of structure, and since the box is not symmetric, and there will be definitely a dependent on the angle. So basically if you look from the top, you will see the f of x comma y be just a box. So in the xy plane, so this is xy plane, you will see this is a function f of x comma y. This is 1 inside and 0 outside. So and you are projecting it to a line which is p distance from the origin and inclined at an angle phi. So since there is definitely an angle dependence, you will explicitly find that in this expression. But similar thing you can try for so this is the rectangular function x comma y, and if you see the Gaussian function, so the similar setup, if you see for the Gaussian function, we have done this earlier, the expression we have evaluated. The Gaussian function is like circles only, or symmetric about the center, but its intensity is basically decreasing outside. So decreasing intensity. So exponential of minus x square plus y square. Okay. So this is the Gaussian in 2D. Now if you say that you are evaluating its a transform on this plane, which is with the p and then an angle phi. You will see any angle theta, you will get the same because of symmetry. You will find that the result is independent of phi. So that's why we got the expression. Let me recall the expression for the Gaussian, which is root pi times exponential of minus p square, right? So which is also a Gaussian. So it will transform to root p times exponential of minus p square. So which is also a Gaussian, which is independent of phi because of the symmetry. Now you can try this another problem. Let's say in the xy plane you have another function which is a circular function, and unlike the rectangular function we have circular function, 1 inside and 0 outside. You try this. So this is actually easier to do compared to the rectangular function. Now you are projecting this, the p and phi. So here also you have symmetry. So you'll find so this is, let's say, so it's actually we can represent, let's say the Heaviside function is theta. We can write it as theta of a square minus x square minus y square, which is centered about the origin and having a radius of a. So you will find, I think the expression is a square minus b square 2 times if mod p is less than a and 0 else. So it's a transform, Radon transform in terms of. So this also you will find. So this you can try yourself. I think this is the solution, which also independent of phi, unlike the rectangular function, which is having a Radon transform, which is dependent on phi, because as you rotate with respect to the origin, you will see there is a dependent on the phi on the distribution f of x comma y. So any questions so far? So other than this topic, like from the previous topic, any questions? Okay, so if no questions, we will stop here for today. So we will meet next week then. Thank you.